Okay. That will take a couple of minutes. Can I take a couple of minutes, or should I discuss it at the beginning of the next lecture? Let me just, I'm very worried about the time, so let me comment on that at the beginning of the next lecture. Thank you very much. Okay, I have a couple of loose ends from last time to tie up before we start today. So, one thing that I was asked was to give this argument that the long time average of these correlators is like e to the minus f or e to the minus f over 2, depending on exactly what we're talking about. So, let me show you the argument for that. So we want to consider long time average of this type of object, where n will be an energy eigenstate that we take to have very high extensive energy, so it's like a thermal state. We'd like to know about the long time average of this thing, so we'd like to compute, let's say, the integral from 0 to t prime divided by t. But that will be, well, that will be, the interesting part will be 0 for this, because it will be alternating in time, the things will be oscillating. So we should take this, and we should take the absolute square. Okay, so we take that quantity, we integrate it over time, and we divide by the interval that we're integrating over. So, let's just write this out slightly more explicitly. N phi m, m phi n, times I. So here I just inserted a resolution of the identity inside one of the factors, and we can do the same thing with the other factor. We need to complicate this one, so we put a star there, and a minus sign. Okay, so now, if we think about the long time average of these two terms, then first we can use the two terms to kill the en. So they have an en in common, those opposite signs, so they're gone. And then let me combine them. Actually, I made a mistake here. This resolution of the identity is with index m. We have a different resolution of the identity over here with index m prime. Okay, so this is minus e prime. We can put that over this exponential like that. So that's our expression. And now if we think about the integral over long times of this quantity, it's going to be 0 if em prime is not equal to em, and it's going to be 1 if em prime is equal to em. So this thing, when we integrate over long time and divide by the time, becomes just a Kronecker delta n prime n. Yep. Okay, this one is m prime and that one is n. Then we get a sum. In this line we have a sum over both m and m prime, but in this line we have a sum only over m. And everything that's left is n phi m, and there's 4 of these factors. So that's the expression for the long time average. So the final step in estimating the size of this thing is to figure out how big these matrixomas are. Matrixoma is the size we can use energy eigenstates. We can do that by looking just at the expectation value of phi squared. This thing should be order 1. But if we insert a resolution of the identity here, we'll get that this is the sum over m of n phi m phi n. Okay? How many terms are there in this sum here? There's one term for each of the energy eigenstates that we're looking at, and the number of those things that are going to be contributing here will be of order e to the f. The spacing between energy eigenstates is like e to the minus f, so there's going to be of order e to the f, or f to the entropy terms of this sum. In order for the expressions to be of order 1, that means that these terms here have to be proportional to e to the minus f over 2. There's two factors of them, so we get the whole thing as of order 1. So we can put that estimate into this expression here. Again, there's a sum over m, which ranges over e to the f values, so we're going to get a factor of e to the f. Now we have 4 factors of this matrix element. So we get e to the minus f over 2, so the 4th power, which is e to the minus f. Okay? That's the long time average of the square of this thing. So the typical value of the 2-point function itself will be e to the minus f over 2. So that's where that comes from. If we've done this analysis not in a particular expectation value of a particular energy eigenstate, but in the thermal state, we would have found another factor of e to the minus f over 2, so the whole thing would have been of order e to the minus f. Okay. The other thing that I wanted to finish from last time is to give you guys a tiny idea of how you can compute this type of commutator squared in a perturbative weakly coupled theory. So actually, specifically, it's nice to consider a large n theory. So in a large n theory, we have many degrees of freedom at each site in the system. There's a nice way to think about Green's calculation, which applies to the case where these operators represent one of the fundamental fields of the theory, where we think of acting as a d operator on the state as inserting an extra quantum, inserting one extra quantum of the large number of quanta at a given state. first dimensional quantum, and actually the language of a disease is very convenient here, the language of an epidemic. So we think about that as inserting one infected particle. This particle can then go and have collisions, interactions with other particles in the system. And every time it has a collision, it infects that particle. The meaning of infection here is just that it affects the state of that particle. So each time it collides with some thermal quantum, we get out two new infected particles in the final state. And actually, there's a third thing which we get, which is an absence of this particle, which would have been present if it hadn't collided with our first infected particle. So each collision takes one infected particle and it turns it into three infected particles. So very roughly speaking, the population of these infected quanta to satisfy the differential equations, which is like the time derivative of the number of infected particles, is proportional to the coupling squared. That's the probability for a collision like this to happen. Times one factor of minus the number of infected. That's saying that if this collision happens, then we no longer have the infected particle in the initial state because it got knocked out of that state. Plus plus three factors of the number. That's the three infected particles in the final state. So altogether we get exponential growth with the 3 and the minus 1 combined to a factor of 2. So in this picture, the number of infected particles is growing exponentially, like e to the 2 minus squared t, where this 2 shouldn't be taken too seriously. Then what is this commutator? The commutator is roughly the probability that the other operator we're looking at will be one of the particles